Let's take the time here to solve some logarithmic equations. So in my previous videos, I talked about a lot about exponential equations. So for example, 2 to the power of x equals 6. And without a calculator, we'd have to think, well, 2 to the power of what is going to give us 6? That's what this x is, right? We're raising 2 to some power, it's going to give us 6. Well, 2 to the power of 2 is 4, so it's going to be more than that. But 2 to the power of 3 is 9, so it's going to be less than that. So it'll be between 2 and 3, maybe 2.3, 2.4, somewhere around there. But if we wanted to get an exact answer, right, this x is in the exponent because it's an exponential. If we take the log of both sides, right, this is really the log of 2 to the x equaling the log of 6 because it's an equation. If we do something on one side, we can do it to the other. We just have to balance it out. Using our log laws, we bring this x out front, so x log 2 equals log 6. And finally, dividing by log 2 on both sides, we get log 6 over log 2, or equivalently, we can write the log of 6 in base 2. So the main idea is that we end up getting an exact answer in logarithmic form. So even though we started with an exponential 2 to the x equals 6, we ended up with a log. Where in these questions I'm going to be going over today, we start inherently with a log. So with exponential equations, the logs we deal with aren't usually super difficult. It's just typically to get the x kind of on the same level as all the other numbers, right? If it's 2 to the x, we brought that x out front. If it was 5 to the x plus 1, we'd bring the x plus 1 out front. But for these questions here, there aren't a ton of exponentials, or any for these ones. We're trying to solve for x when they're already inside the log. So the first thing I'm going to do for part A here is I'm going to, like these two logs are adding together here. I'm going to add them together and make them one logarithm. So this is the same as the log in base 4 of 2 times, if we use our log laws, bring that 3 to the exponent on the x, it'll be 2x cubed. And that's going to equal the log in base 4 of x. So now that we have this, there are kind of two ways we can think about it. We can say, okay, well, this is the log in base 4, that's going to equal something. This is a log in base 4, that's going to equal something. But how can we kind of get rid of that log? Because logs are kind of ugly in equations. Well, what we can do is we can take the inverse log, or the anti-log, and we can go 4 to the power of log in base 4 of 2 to the x cubed. And that'll just give us 2 to the x cubed, because the inverse log in base 4 is just 4 to the power of that log. And I know that's a lot of kind of random inverse mathematical terms. The way you can think of it is this is 2x cubed inside the log in base 4, and that equals x inside the log in base 4. So because these are both inside the log in base 4, right, the log in base 4 is the same. And if they equal each other, that must mean that the things on the inside must equal each other. Because everything else is the same, the only difference is the inside. But they equal each other, so we can just say, okay, let's forget about the logs. 2x cubed must equal x. Because if that's true, then this equation holds true. So what we want to do is we want to try and get both, like the logs on both sides in the same base, so we can compare the arguments, and the argument is just the number inside the log. Okay, cool. Now we don't have any logs at all. We're kind of going the opposite direction. With exponentials, we ended up with logs. Right now, we're kind of getting rid of them. Now this is a polynomial equation. So we have an x cubed, we have an x. Well, if we subtract x on both sides, just for space sake, 2x cubed minus x equals 0. Well, we can factor out an x. We get 2x squared minus 1 equals 0. So we have these two solutions here, either x equals 0, right, because they're multiplying to give us 0, or 2x squared minus 1 equals 0. Because if either of these are 0 and they're multiplying, we're going to get 0. So we just set both of these equal to 0. So obviously x equals 0, we already solved for x. So that's one of our solutions. Another one is we add 1 on both sides, so 2x squared equals 1. We divide by 2 on both sides, so x squared equals 1/2. And then we square root the top and the bottom to get x. So this is 1 over the square root of 2, which is the same as the square root of 2 over 2 if we rationalize it. And you might also recognize that as the sine or the cosine of pi over 4, 45 degrees. But in the end, x is equal to 0 and root 2 over 2. And whenever we do these questions, we have to make sure that when we plug those x values back in to the logarithms, they're either, they're greater than 0, because the log of 0 doesn't exist. Okay, the log of 0 doesn't exist, so since we got x equals 0 for a solution, we actually have to neglect that. And root 2 over 2, that's a positive argument. So as long as the argument inside is positive in the end, then that means that we're good. And mind you, your value for x doesn't always have to be positive, because let's say this was x plus, let's say we were taking the log of x plus 3. Let's say x was negative 1. This would be the log of negative 1 plus 3. This would still be the log of 2. So the argument as a whole is 2. The x is just negative 1, but your x can be negative in some cases, so just remember that. Okay, let's do part B here. I'm going to move this over a bit. Maybe shrink it down. Here's a solution there, root 2. The log in base 5 of x minus 1 plus the log in base 5 of x equals the log in base 5 of 6. So they made it pretty easy on us. They gave us everything in terms of the log in base 5. Well, great. That means that we can use our log laws. Let's multiply these two together because they're adding. So this will be the log in base 5 of x times x minus 1, which will equal the log in base 5 of 6. So the log of x times x minus 1, well, that's just the log in base 5 of x squared minus x, which equals the log in base 5 of 6. Well, this is exactly what we had in the last situation. We can take 5 to the power of this log in base 5, or we can just say, well, these are both base 5 logs, and if the whole thing equals the other side, then the insides must equal each other. So we can just say x squared minus x equals 6. Right? Because if this is true and we plug this back in, well, there's an equal sign here telling us that this is true because everything else is the same. The log in base 5 is the same. And if these two sides equal each other, x squared minus x has to equal 6 because those are the only two things that look different. Okay, so now this is a quadratic, right? A polynomial equation. Get it equal to 0, x squared minus x minus 6 equals 0. Two numbers that multiply to negative 6 and add to negative 1. That's going to be x minus 3, x plus 2 equals 0. Our two solutions will be x equals 3 or negative 2. Now let's just check if that is all right. If we plugged in 3 for x here, we would get the log of 3 minus 1, which is the log of 2, and the log of 3. So those are positive, which is good. And if we plugged in negative 2, we would get the log of negative 3 and the log of negative 2, which does not work because we need a positive argument. So we neglect that answer there. Okay, 2 is equal to the log of x. Okay, so for this one, when we don't have a log kind of everywhere, we have a logarithm. This is a single logarithm, even though there's kind of a log inside it. That just equals 2. So anytime you have a logarithm equaling a number, it's probably beneficial to get this in exponential form. So the imaginary base on this logarithm is a 10. So another way to write this is just saying 10, this base, to the power of 2, what it equals the argument of the logarithm. So this is the log of x, because this log x was the argument of the initial outside logarithm. So 10 squared is log x. Instead of 10 squared, I'm just going to write 100, because that's just 10 times 10. Well, we have the exact same thing again here, right? We got a log inside a log. We got rid of one of them. Now we're going to do the exact same thing, because remember, there's a hidden 10 there. So we get this in exponential form. We say, well, this base 10 raised to what it equals, 100, equals the argument, which now is just x. So x is equal to 10 to the power of 100, which is an absolutely huge number. It's it's 1 with 100 zeros after it, which is just massive. But if you were to put that into this equation, right, the log of that as your argument of the log will just give you 2. Okay, so now let's do part D here. So they did a bit of factoring action. Let's see what we got here. So we got the natural log of e to the 8th minus, okay. So what I'm going to do is I'm going to distribute this a half, because I never like when a constant factor is factored out in logarithms. I like to apply it and use our exponent law here. So this 1/2, this is the same as 1/2 ln e to the 8 minus a half ln 4x squared, right? If we use our exponent laws, we say, okay, we're taking that to the power of a half, right? So 1/2 ln of e to the 8 is the same as ln of e to the 8 raised to the power of 1/2. So these exponents are multiplying. This is just going to be the ln of e to the 4th. Ln of e to the 4th. Okay, and remember the natural log is in base e. This is just log in base e. So if we say the log in base e of e to the 4th equals some number, well, this base e to the power of what it equals the argument. So this other side must equal 4, right? Because if we take e the base and raise it to the power of 4, we just get e to the 4. So actually this first term, we don't even need to leave it as a logarithm. We can just say it equals 4. This equals 4. And another way we could do it is we could just say, well, e to the 8, the natural log of that will just give us 8, and taking a half of that is just a half of 8, which is 4. That's another way you could do it. And if we have this natural log here, remember, we're saying minus the natural log of 4x squared to the power of a half. Well, this half is distributing into both of these. 4 to the power of a half is just the square root of 4, which is 2, and then x squared square rooted is just going to give us x. So this is the natural log of 2x. Okay. So now what we have is equal to 4. Okay. So now that we have kind of this figured out, minus the natural log, yeah, that's looking good. Now, see how we have a 4 on both sides? We can cancel this out. So we're going to get negative natural log of 2x equals 0. Because if we subtracted 4 on both sides, we just get 0. Also, we can get rid of that negative by dividing by -1. So since the other side's 0, it doesn't really change anything. So the natural log of 2x equals 0. Now let's get this into exponential form. So remember, the natural log is really just the log in base e, right? That's the same thing as the natural log. So we can get this into exponential form. Remember, 0 is a constant. If we have a log equaling a constant, we always get it into exponential form. So this base e raised to the power of what it equals, which is 0, equals 2x. Okay, now if we know what e to the 0 is, right? E is just a constant, 2.718, blah, blah, blah. To the power of 0, anything to the power of 0 is 1 equals 2x. Divide by 2, we get x is equal to 1/2. Okay, now if we plug that into our original equation, just make sure it's greater than 0 here. If x was equal to 1/2, we would get 4 times 1/2 squared, right? So that'll be 4 times 1 over 4, which is equal to 1, which is fine. So that's going to be the natural log, blah, blah, of 0. Yeah, it looks good. So if x is 1/2, the argument's never going to be 0 or less than 0. Cool. Now let's look at this one here. Okay, so more of the same kind of stuff. This is a log in base 9, log in base 9 equal to 1. The first thing I would do is, let's actually combine these logs first and see what we can do from that. So remember our log laws, this is the same as the log in base 9 of x times x minus 8, that equals 1. Okay, there are a couple ways we can do this. Remember how I said in a lot of these questions, if you have a log equaling just a constant, get it into exponential form, you can certainly do that. So you can say, well, 9 to the power of what it equals, which is 1, so just 9, equals the argument, which in this case it's x times x minus 8, so I'll write x squared minus 8x. But another way you could do it is you could say, okay, I have a log in base 9, and I have a constant. How can I get this constant 1 as a log in base 9 and just compare the insides? Well, the log in base 9 equaling 1, that's the same as the log of 9 in base 9. Right, so now that they're both the log in base 9, you can say, well, now the insides must just equal each other, and that's also how we get this part down here. So 9 is equal to x squared minus 8x. Okay, so now what we want to do is move that 9 out of the way, get one side equal to 0. Okay, and now we just factor. So 0 is equal to x minus 9, right, and x plus 1. So that means that x must equal 9 or negative 1 if we set them equal to 0. And plugging both of those back in, if we plug 9 in, we'd get positive arguments. If we said x was negative 1, well, this would already not be like a valid answer because we can't have the log of negative 1, and this would be the log of negative 9. So we're going to reject negative 1 and just keep positive 9 as our value for x. And that happens a lot for logarithms. Either you're going to cross out one or two of them, but very rarely you keep both two of them. Okay, so what do we have here? Okay. So the first thing that stands out to me is that we have a squared, a linear, and a constant term. Okay, so actually I'm gonna move this one over because we have two constants. I don't like how they're split up. Let's just say minus 6 equals 0 because we can just move that over. Okay. So notice how this is x plus 2 in the log, x plus 2 in the log. Only difference is there's a squared here. So what if I said let's say, I don't know, some value, well, my name's C. So let's say let C equal, or my name's Callum, so my name starts with C. If I'm ever trying to think of like a variable that represents something, I just choose a random letter. Let's go with C. Let's say C equals the log of x plus 2. Okay, well that simplifies that a lot because this notation here, log squared, really just means the log of x plus 2 all squared. Well, if the log of x plus 2 is equal to c, and we're squaring the log of x plus 2, we can just write this as c squared. So c squared, and then plus the log of x plus 2, so just plus c, and then we have minus 6, that's kind of independent of the log, equals 0. Remember, this is something we can factor. So if we factor this, we need two numbers that multiply to negative 6 and add to positive 1. We get c, let's see here, plus 3. We get c minus 2, perfect, equals 0. Well, now we know c must equal negative 3. C must equal positive 2. I don't need to write the plus, I'll just write 2. And once we always do these substitutions, remember, C doesn't mean anything. If you do this on a test, your teacher's going to say, great, you're kind of partway there, but C doesn't have any meaning to me. I don't even know what that is, other than you kind of declaring it up here. So once we solve for C, we have to substitute this log back in. So the log of x plus 2 equals negative 3. Right? C doesn't, well it does, but C doesn't really mean anything. We have to say that this log equals negative 3. Same idea over here. The log of x plus 2 equals positive 2. So solving them individually, remember this is log equaling a constant. We can get this into exponential form. So 10 to the negative 3 equals x plus 2. So we can just say x equals 10 to the negative 3 minus 2. So that's going to be about minus 1.999 or something. And then for this one here, we can just say 10 to the power of positive 2 equals x plus 2. Well, 10 squared, 10 to the power of 2 is 100. So minus 2x is going to be 98. So let's just plug that back in, see if it works. Yeah, it's going to work for both of them, because if this is, actually I think I have my calculator here. So 10 to the power of negative 3, that's like 1 over 1,000. So yeah, it's going to be 0.001. If we take that and we minus 2, it's going to be negative 1.999. But notice how if we put negative 1.999 back into here for x, we're still going to get negative 1.999 plus 2, which is a positive 0.001. Even though it's really small, it's still positive. So this one's good, and this one is also good. So we're going to leave both of them in this case. So that kind of concludes my 6 questions going over solving logarithmic equations. I hope this was helpful. It's not too different from our exponential problem solving, but just a little bit different in that the logs can get a bit trickier in how we kind of approach them, because we're given the log first as opposed to having to solve for x a different way when it's already in the exponent. So not a ton of exponents here, only when we convert it back to exponential form, like in this case right here. So yeah, I'll see you in my next video, and thanks for tuning in.